Good afternoon. Thank you for presenting me. My talk is about comparison capabilities of Sonalleve V1 and V2 MR-HIFU systems for generating nonlinear fields with high-amplitude shocks for histotripsy type application. So Sonalleve MR-HIFU is a therapy platform which is used for different clinical indications. And the physical mechanism is the volumetric heating. The system operated with continuous waves in the framework of linear acoustics. But recent studies have shown that this system could also be successfully used for mechanical tissue ablation using Boyle histotripsy technique. This approach uses millisecond-long pulses with high-amplitude shocks delivered at low duty cycle to produce vapor bubbles within each pulse to mechanically liquefy tissue as shown in photos for ex vivo bovine liver. Acoustical characterization of Sonalleve V1 system showed that this system is capable to generate shock fronts with an amplitude more than 100 megapascals, which is sufficiently for Boyle histotripsy. Recently, Sonalleve was updated with a new therapeutic array transducer, which still comprises 255 elements of the same 6.6 millimeter diameter, but distributed in a different manner. Instead of uniform quasi-random distribution, the array is divided into 8 sectors. And the shell has slightly larger diameter and longer focal distance, so the new array is less focused now. But our previous studies show that the amplitude of the shock front is strongly dependent on the array geometry. So the goal of this study was to characterize the new Sonalleve V2 therapeutic array in order to evaluate its capability to produce shock waveform at the focus required for shock-based treatment like Boyle histotripsy. Both arrays were acoustically characterized in water using numerical simulation and measurements. The boundary condition in numerical simulation was set using acoustical holography hydrophone measurements. Then linear simulation was conducted and showed that new therapeutic phased array Sonalleve V2 has longer focal lobe along the axial direction Z than the previous version. Thus, nonlinear acoustic effects should be different for the Sonalleve V2 ultrasound field. Then nonlinear simulations were performed for increasing power output of the array. Presented below are focal waveforms with developed shock front for both V1 and V2 system. Developed shock front is defined when its bottom value is equal to 0 pressure. That is, the shock amplitude is equal to the peak positive pressure. It was obtained that in older system, the amplitude of the shock front is 92 megapascals, while in the newer system, it's 10 megapascals less, only 82 megapascals. These slides demonstrates more detailed characterization of focal pressure obtained in increasing power of the array. These results are presented for V1 system, and with increasing power of the array, initially the peak positive pressure increased linearly, but when it's iterated because of enhanced absorption due to presence of shock front. For the newer system, you can see that the peak pressures are lower than for the previous system for the same power of the array. And the shock front of 82 megapascals is generated at 20 lower output of the array. So these differences in generated shock front of both Sonalleve systems should be taken into account in development treatment protocols for shockwave exposures such as Boyle histotripsy. Thank you very much for your attention.
Questions from the floor?
So simple questions, though. Compared to the V1 and the V2, it obviously is going to be harder to do Boyle histotripsy, but what are the limitations? So it looks like you still will be able to do it, but what are the limitations based on your calculations?
Actually, we're still able to produce histotripsy, but we are quite close to the higher boundary, to the higher power, output power of the new array.
So then you probably, for deeper targets, it might not be as effective, correct?
Yeah,
Did
right,
it?
right. In tissue, when we performed derating, yeah, if it's quite deep tissue, yeah, it will be challenging.
Okay, thank you.
Thank you.
How does it change with the axial focus? I mean, you can electronically modify the focus depth, right?
There is possibility of moved focused electronically. So the steering is about 8 millimeters, so it's possible.
No, not
to-
left-right, actually.
No, the focus is fixed.
It's fixed?
It's fixed, yeah.
Okay, thank you very much. We'll move on